Alright, so in this video, I'm going to be explaining another approach for domain adaptation, and we use it for graph transfer learning. And domain adaptation has many variations. The most difficult one is unsupervised, and after that, semi-supervised. In semi-supervised, when we have some label data in target domain as well, and we have fully supervised, which is not very important because it is already solved. There is nothing challenging, and there are many other approaches. So let's focus on this article in 2023. As in a specific case of graph transfer learning, unsupervised domain adaptation on graphs aims for knowledge transfer from label-rich source graphs to unlabeled target graphs. However, graphs with topology and attributes usually have considerable cross-domain disparity, and there are numerous real-world scenarios where merely a subset of nodes are labeled in the source graph. This imposes critical challenges on graph transfer learning due to serious domain shifts and label scarcity. Because some target graphs are unlabeled, and we want to have a good knowledge transfer. Because in the source graph, you have very good label-rich data, you have many of them. So we want to see how can we use this transfer. So to address these challenges, we impose a method named semi-supervised graph domain adaptation. To deal with the domain shift, we add adaptive shift parameters to each of the source nodes, which are trained in an adversarial manner to align the cross-domain distributions of node embedding. Thus, the node classifier trained on labeled source nodes can be transferred to the target nodes. To address the label scarcity, we propose pseudo-labeling on unlabeled nodes, which improves classification on the target graphs via measuring the posterior influence of nodes based on their relative position to the class centroids. So this is the semi-supervised domain adaptation. That in the source graph, you have some labeled nodes, but on the target graph, there is no unlabeled nodes. This is one way that you can formulate semi-supervised, but this is not the only way. So there are two issues: how to overcome a significant domain shift across graphs to give domain invariant predictions. The domain shift between the source and target graphs roughly lies in the following two views: graph topology and node attributes. For example, distinct graphs may have different link densities and substructure schemas, and handcrafted node attributes from diverse sources could have significant biases individually. This brings more considerable domain shifts than traditional data. The second issue is that how to mitigate the label scarcity for the classifier to give accurate and label discriminative predictions. Since the target graph is completely unlabeled, existing work only performs domain alignment, without considering the situation that the overall distribution may be aligned well, but the class level distribution may not match the classifier well. So we have a source graph. This A is adjacency. So if there is a node, it's 1 for each of the entries of this matrix. And so the target graphs is like this adjacency in your data. So the problem of semi-supervised domain adaptation is that given this source graph with very limited data, that's why we are saying that it's semi-supervised, very limited labels in the source domain, and the target completely unlabeled, and they have certain domain discrepancy on the data distributions but share the same label space. And the goal is to learn a model to accurately predict the node classes in the target graph with the assistance of partially labeled source graph. So we give the source graph into this line, the target graph into this line, and all of them are, as you see, they are convolution. This is the framework of SGDA. And the source graph and target graphs with reconstructed high-order topologies are fed into two-layer graph convolutional network. So these are graph convolutional networks to generate node embeddings, where source graphs are added with just these shift parameters, because in the source we add also the shift parameters to promote distribution alignment. Three losses perform supervised learning: domain adversarial transformation via shifting and pseudo-labeling with posterior scores. So we have three modules: node embedding generalization to sufficiently explore high-order structured information to both graphs to learn generalized node representation. The second one, adversarial transformation. And the third one is pseudo-labeling with posterior scores. So we propose pseudo-labeling loss on all unlabeled nodes across domain, which improves classification on the target graph. We are measuring the influence of nodes adaptively based on their relative position to the class centroid. Node embedding generalization. So given a graph with adjacency, we use random walk to sample a set of paths on A and obtain co-occurrence of frequency. And this f sub ij accounts the time of the nodes nj occurs within a predefined window in nodes ni's context. Then the positive mutual information between the nodes is computed. And so this Pij, this is the probability of the node nj occurring in the context of node ni. And these probabilities, P sub I, P sub j, are the probability of the nodes ni as the anchor and node nj as the context. So Pij is the positive mutual information between n sub I and n sub j, which reflects the high-order topological proximity between nodes. So if two nodes have high-frequency co-occurrence, P sub ij should have greater than if they are expected independence. We can obtain a mutual information matrix as a new adjacency matrix of G. So the ELF graph convolutional layer is defined like this. And sigma here is just the activation function. So given the source graph and the target graph, we first add the shift parameters to the source graph and obtain the shifted source node embeddings with the distribution H, S, and C. And H is the output function. So the optimization is to make the distribution similar to the target. So we define the shift parameters as randomly initialized multi-layer parameter matrices. So these shift parameters are matrices, they're not just scalars. Then we can obtain the shifted source node embeddings. And we propose adversarial transformation objective on the source node embedding and target node embeddings. So this is the pseudo-labeling with posterior scores. We define the classifier on the node embeddings to model the label probability of nodes, which is a multi-layer perception followed with a softmax layer. Then we can obtain the probability of each node in the source graph and the probability of each node in the target graph. Since only a few nodes are labeled in the source graph, whereas all nodes are unlabeled in target, the model will be easily overfitting if we just use this equation. So without any supervision, the nodes in the target graph distributed near the border and far away from the centroid of the clusters of their corresponding classes are easily misclassified by the hyperplane learned from the label information of the source graph. Thus, we propose pseudo-labeling strategy with posterior scores of nodes to improve the prediction accuracy on unlabeled nodes. So in each training iteration, we update the pseudo-labels for the unlabeled nodes in both the source and target graph by mapping their output probabilities into one-hot encoding. So this is our one-hot encoding, and M is just the one-hot map. And P sub I is the probability of node N sub I. So we treat all unlabeled nodes cross-domain in the same level and omit the notations of domains, superscript for brevity. So we introduce a posterior score to define how N sub I is close to the structure centroid of a pseudo-label cluster on its reconstructed adjacency matrix P. So then we apply a cosine annealing function to scale omega sub I into a certain range. Then we define a pseudo-labeling loss function with posterior scores as follows. So we just combine the three losses. And the shift parameters are optimized by projected gradient descent.